In this video, we'll be once again looking at the shell method. Determine the volume of the solid obtained by rotating the region bounded by x equals 9 minus y squared, x equals 0, in the first quadrant about the x-axis. So our step one is to once again look at x equals 9 minus y squared. Keep in mind that this function, if we were to graph it in the y equals 9 minus x squared case, would have a point up here at 9 and it would be facing down. However, because we're looking at x equals 9 minus y squared, that function will now start over here in the positive x-axis at the value of 9, and it'll be facing down towards the negative x-axis. So this is the function that this is actually going to be looking like. We're going to have x equals 0, which is here, and we're in the first quadrant. So that means that we're going to have to go ahead and use the y-axis and the x-axis, and assume that we're looking at this space right here, not that space there. With that being identified, we're going to go ahead and take that region right there and we're going to revolve it around the x-axis. So our first step here is to actually just go ahead and draw this function. Nice big section. We're going to rotate it around that x-axis. Now I'm not going to go ahead and revolve it in this first image. This first image is just going to help me simply identify the region I'm playing with. This intersection point is 9, 0. This intersection point here is if I'm going to go ahead and plug in a y value for this location here and get back 0 for x, that value is going to be 3. So 0, 3, and then don't forget we have 0, 0. So those are all the intersection points of that particular region. Now I'm going to go ahead and take that region and I'm going to revolve it around the x-axis. Doing so will make it look something like this. And you'll notice as I'm drawing my circular cross sections that this is the way that the object is going to appear. Now keep in mind we're attempting to use the shell method. So the fact that this is revolving around the x-axis means that I actually want to cut it horizontally. So that means I'm going to cut this region like this. Now, my goal is to go ahead and set up the integral for volume. And the integral for volume, if I'm cutting it horizontally, will be a y equals. Since I'm starting with the y values, I'm going to go a y from 0 up until 3. Again, my lowest value in the region is 0. My highest value in the region is 3. In respect to dy, the formula that always is going to be inside here is 2 pi rh. Again, the reason why it's 2 pi rh is because it's going to be a rectangular cross-section. Again, we're slicing this thing in such a way so that it gives us this circular object, but then we unravel it. Again, like a roll of toilet paper, we unravel it. So every single cross-section is going to be a rectangle. That rectangle is going to have a height of h and a length of 2 pi r, the circumference of the circle that is created. So with that being identified, I now just need to figure out what r and h will be. In terms of the height, the best way to think about it is that the height is going to go from this dot here up into this function here. Now in most cases that height ends up being either some form of f of x or some form of f of y. It entirely depends upon what kind of function we're looking at. Now that height might also change based on if there's multiple different functions in here. But in this case, I'm just looking at the height going from this axis up to that function. Now that function, remember, is x equals 9 minus y squared. Okay, so if that's the case, that means my h is simply going to be a distance of x. Again, notice that is a distance of x from here to here. That's a distance of x is equal to 9 minus y squared. So that's what's going to be plugged into here. Now we got to figure out what our r is. Well, keep in mind the r is going to start here at the rotation axis, and as I rotate this object around, the r is going to go from here up into that location. Notice that that location right there is actually a distance of y. So again, we have a distance of x and a distance of y. The distance of x is entirely coordinated based on our function. Our distance of y actually seems like it's more arbitrary than anything else, which means that it is going to be nothing more than the variable y. Now keep in mind that this y is going to change based on the same concept of our shift in the rotation axis. So because we're around the x-axis, it is simply y. If it was rotated around a different axis, say x equals a -2 or x equals to a -5 or x equals even to say a 4, that's going to change this rotation axis to be either r equals plus or minus, y plus or minus a number in some form or another. But in this case, because we're revolving it just around the x-axis, I have 2 pi My r value is the function of y, which is again just y inside the integral of dy. And my h is the function that we obtained from the distance of the axis to that location. So this right here is the setup for the integral of the volume of this object created by rotating this space around the x-axis. To simplify and evaluate, you will be nothing more than factor out the 2 pi. I will distribute the y into the problem, giving me 9y minus y cubed dy. And from there, the integration should be relatively straightforward.